So we will come to the last lecture of Perron's method. In the previous lecture, we have seen the existence of a harmonic function, and we do not know whether that harmonic function will satisfy the boundary values g, but we know that u is less than or equal to g. But to prove that u equal to g requires some conditions on the boundary, and that is what we are going to introduce now, what is called the regularity of d omega. Okay, so that we are going to define what is the regularity of d omega today. So analyze the boundary. So this is basically the boundary analysis now. Boundary analysis. So let me define what is a barrier. So I am going to give a definition of a barrier or barrier function. You can call it that. Barrier function. Okay. So let psi belongs to d omega. A function w in continuous function up to the boundary is called a barrier at psi. Okay, barrier at psi relative to omega. So this is what you understand, relative to omega. Okay, if w satisfies the following, one, w is subharmonic. It's important. 2, w psi equal to 0. At that point w psi equal to 0, and in other points you want w of x less than 0 in omega bar minus. Okay, so in a domain here is called a barrier at some point psi. Here is psi. So at this point w psi equal to 0, and all other points where wx is less than 0, and it's also subharmonic. Okay. In fact, this you will see that it's actually a local issue, because you are basically defining a neighborhood of that, and so I will give a definition now. And you will see that its existence of local barrier is good enough. Local barrier. Okay. Again, a function w bar belongs to c omega bar is called a local barrier at psi. So it's nothing relative, that called a local barrier at psi in d omega if there exists a neighborhood n psi of psi such that w bar is a barrier relative to this neighborhood actually, but neighborhood may have also a relative to n psi intersection omega bar. So that's how you are looking at it. So you may have a neighborhood here, n psi. So you are looking this barrier relative to this neighborhood. So you are looking at that. It's enough to have a barrier here. So every point this neighborhood can change, then that's what is called the axis. So you are not demanding the existence of W for all omega, but this existence only in that neighborhood. But what I'm going to an immediate claim, so the immediate claim, okay, so local barrier implies global barrier, basically. Local barrier, so it's a local concept, implies global barrier. So if you can find W bar, global barrier, okay, but global barrier relative to omega, you can say. So the proof is actually easy, so you can just check this. One can verify easily these concepts without any much trouble. Okay, so you have this one. Let W bar be a local barrier. W bar be a local barrier at psi in d omega. Then what you define that m is equal to the supremum. So I will not verify everything, you can verify. So what you do is that, so first you take a neighborhood. So this is your psi, this is your psi, and you have your n psi here. On that you take a ball here first. This is a B. So I will take, so what you will do is that, so your B is contained in N psi, and of course psi is also in B, a ball centered at a ball centered at psi. So you can take this ball. So you are taking supremum. So to understand this supremum, the W bar of psi equal to 0. So you see W bar of psi equal to 0. So at this point W is positive, but then W is negative everywhere. So in particular W bar is negative here, strictly negative there, and you have your closed bounded set here. Your W bar is negative. So I can take this supremum, which is a finite quantity, and I can define the supremum in n minus b. So I am defining, this is your n psi minus b on that, and then you can define your you just define. So I don't know, unnecessary things that came up here. Okay, so define. So yeah, your W of x is equal to maximum of, so I am defining via maximum, so you don't lose your subharmonicity. W, see this is a negative quantity, you have to see that it's a strictly a negative quantity, because W bar you are defining here and it is a negative in a thing, so the supremum material as a strict negative quantity, so that m is negative. So I will define, this is a continuous way of defining something, so I will define maximum of n. So when at W at psi, W psi is equal to 0, so m is strictly, so this you get immediately W of psi is equal to 0. All that verifications you can easily do. This I will define, x is in omega bar minus b, and omega, sorry, inside part. Okay, so I will define, this is omega intersection b. Okay, so this is your omega intersection b, and at psi your W psi is equal to 0, m is strictly negative, you get W psi. So you can verify all this property, and outside that I will define to be m. Okay, m for all x in omega bar minus b. So I can extend this function as a continuous function and taking this all w, so that maximum, and then defining this way, I will retain my w as a negative function, and you also get this is a subharmonic. It's easy to prove that it's a subharmonic because I'm taking maximum of a constant function and a subharmonic function, and then the defining this value. And w psi is equal to 0 is trivial, and then by maximum whatever it is, you can prove that m is less than 0 everywhere, w is less than 0. You can also show that w of x is less than 0 for elsewhere. So this implies w is a w is a barrier at psi relative to omega. So whenever you have a local barrier, that gives you automatically a global barrier. So it's enough to see whether thing. So this gives my definition of a regular thing. So you have your definition. Okay, barrier function, you can call it existence of a barrier. If barrier function exists, it's called a regular domain, or it's a regular domain. Regular domain. Okay. So if such a barrier exists, you call it regular barrier. So a boundary point psi in d omega is called regular if there exists a barrier. It doesn't matter local or global now, right? Because the moment you exist local, you barrier at psi. So whenever there is a barrier function exists, that's a negative subharmonic function basically. Okay, then it's called a regular point. If all points, a domain is called regular, if all boundary points are regular points. If all boundary points are regular points. Boundary points are regular points. So you see the point. That's my definition of regularity of the domain for the time. Of course, you may be able to give a sufficient conditions for such regularity. Okay, if you have other kind of good definitions of the regularity of the domain, that will imply some, not all, but one sufficient condition, maybe I will look. So under this regularity, we show ux equal to gx, the ux defined earlier in the last class, equal to gx for all x on the boundary. Okay, so let me write it as a theorem and then start proving it. Again, it's not very difficult, but you need to cleverly use the theorem. Okay, let g belongs to continuous function at the boundary, on the boundary, and u be the harmonic function defined earlier, be the harmonic function, which we already proved it, harmonic function defined earlier as, how did we define? Ux equal to supremum of v of x, where v is in SG. assume psi belongs to d omega is a regular point. Then that is how the boundary values are always defined via the limiting process, because u is defined inside, not at the boundary necessarily. That's enough. Then ux converges to g psi as x tends to psi. So you have a domain. This is how the boundary value problem always indicated. So you have a psi. If psi is a regular point, you take x converges to z, x converges to psi. So for all these x interior, your ux is defined. So you proving that ux converges to g psi. That's how your boundary values are always interpreted. So let me try to give a proof of this fact now. Not very delicate, not very difficult, but as I said, the proof involves some amount of work. So let me call this d omega is a compact set. You have your m is equal to supremum of mod g, where on the boundary this is a finite quantity, so that is not a problem. And w be a barrier at psi, because you are given psi to be a regular function, regular point. There may be many barriers, that's not a problem. Barrier at psi, okay, psi in omega. So to prove that one, so you know that w is so since now w since you know that w psi equal to 0, okay, that fact you know that g and w is continuous, so you have all these fact, you get g is continuous, all these are all at psi continuous. Therefore for given epsilon, so use this thing, given epsilon proper greater than 0, there exists delta positive such that w psi is equal to 0 and w is small enough, so wx is small enough such that modulus of w of x less than or equal to epsilon, less than or equal to doesn't matter, for mod gx minus g psi less than or equal to less than epsilon. This happens for all whenever mod x minus psi is less than equal to delta. You see, that's what. So let me put this figure once again here. So you have psi and then you have an x minus psi. This is your sig, this is your delta. So whenever x is here, so this is where your x here, x belongs to this set, and your gx, because g psi and w psi is equal to 0, so this you can make small enough. Now w is a nice continuous function. On here g is w is negatively bounded, right? G is less than 0 on this set, okay? So here you get g is w is negative, so it will have a negative maximum, okay, because it's a bounded and in a bounded compact domain on here, so it will have a, so I will write that you can prove that w on this domain mod x minus xi greater than or equal to delta, you can actually show that w is less than or equal to some minus c with c positive. I will write that in a slightly different way, therefore you can also see this. So therefore there exists, I write it something like that, k. This is a different way of writing that, but you can prove this even. This thing because I need the kw of x is greater than or equal to m for all mod x minus psi greater than or equal. That's trivial because I'm only demanding w of x. See, this is a minus sign, so w is negative. You see, so that if I divide this, you get you know that w is less than or equal to some minus c. Okay, I'm rewriting that in this form. That's all. you can choose some k sufficiently large enough so that w is negative, so this is a positive quantity. Okay, so this is a positive quantity. This is a positive quantity, and you can choose large enough so that it is greater than or equal to m. Now I construct two functions. So let me construct two functions. A v1. So I construct two functions. v1 is equal to v1 of x is equal to, so using that is just a small trick, it's not a big trick, is equal to minus k with that kw, and I also define v2 gx plus epsilon, not gx, so sorry, x comes here, this is a fixed quantity, so I will have here minus epsilon plus k. These are all when you such tricks are used when you deal with sub and super harmonic functions. So this is v2. So you can immediately see two things from here. If you compute your Laplacian of v1, because these are all constant, you will immediately minus k Laplacian of w, and w is subharmonic, so this is positive, so minus of that will be negative, and Laplacian of v2 is equal to k Laplacian of w, that is greater than or equal to 0. So this implies v1 is superharmonic, and you can also immediately verify. Let me not do everything because today will finish. You can actually show that v1, this is very easy to show, so I'll get v1 is greater than or equal to gx. Okay, similarly v1 of x, okay, on the boundary, okay, and then v2 is, that's true because of the m you will get it, okay, so v1x is basically, you can show that this is actually, let me do, maybe if you want to do, this is g of psi plus epsilon, this is greater than or equal to m, so you will get this is equal to m, greater than or equal to, and this is also less than or equal to, you can show that this is less than or equal to minus m, right, g psi minus epsilon minus m, you can use this minus epsilon minus m, so this is a, you see, because kw is less than or equal to minus m, so you will have this thing, use this one because m is the supremum, you can get this fact. So v2 is subharmonic and v2 is less than or equal to g. So v2 is in sg, minus v1 is also in sg. That's what you are using. So it's a superharmonic, so minus v1 will be subharmonic and minus v1 will be less than or equal to minus g. So that fact we will not use it. It's a superharmonic function. So v1 is v2 is a subharmonic function, v1 is a superharmonic function, and we also can easily use these facts to show that v1 of x, so v1 is this one, we can actually show that v1 of x is, use these facts, all the whatever described here, you can show that this is less than or equal to ux and less than or equal to v2 of x. This is easy to show for all x in omega. So now you write down your v1. So we write down your v1 from here. So you see, you write down your v1 from here. So v1 less than or equal to this, so you can take your g psi here, and this you can estimate exactly. So that will imply immediately my v1 of u of x. Please write down these steps. I think my g psi is less than or equal to epsilon minus k. That wm you don't need for this, so that's it. So I have just taken g psi here from v1 and v2, so that one. Now look at it, as x tends to psi, epsilon is arbitrary, and wx goes to w psi, which is 0, as wx goes to w psi. is equal to 0, that implies ux converges to g psi, and that's what you want to be proved as x tends to psi. Okay, x tends to psi. Yeah, so thus we have, so that proves the boundary value thing. So thus we have the, so that is proved. So we have the final theorem, basically existence, and we have the final theorem existence and uniqueness. Uniqueness we already proved. Now existence is also proved. Existence and uniqueness. Okay, we'll prove that one. Okay, so let omega be a bounded domain. So let me write it in this line. Let omega be a bounded regular domain. So every point is a regular point. Bounded domain with the regular boundary. Regular boundary. Then, okay, boundary d omega. Let G belongs to C of d omega. Then there exists a unique solution. Then there exists a unique solution to the boundary value problem, to the boundary value BVP minus Laplacian of u. Okay, doesn't matter because we are dealing with Laplacian of u equal to 0 in omega and u equal to g on d omega. So whenever you have regular thing, but then there is a converse part. That's what I said, the regularity which we have defined is also thing. So conversely, if the above, so let me call it 1 here. If 1 is solvable for all, if 1 is solvable, the converse is easy to see. Solvable for uniquely for all continuous G, for all G continuous, for all G. For some G may be solvable. Suppose you want solvability for all G continuous, then omega is a regular domain. You see, so the regularity we define is an event only if condition for solvability for every G is a regular. Of course, even if it is not regular, for some G you may get it. You take any solvable, any problem. If suppose you take any solution of Laplacian equal to 0, it will give some boundary condition. So naturally it satisfies such equation. So proof is trivial now. One part is proved. Okay, so assuming that omega is a regular domain, this is what we have done now. Conversely, if one is solvable for all G in continuous functions, okay, then consider this particular G. Consider Gx equal to minus mod x minus psi. Okay, let x is in psi is in d omega. You want to show that omega is regular, so you want to show that every point psi in d omega is a regular point. So start with psi in d omega, consider this function. You see this is for x in d omega, so g psi equal to 0. You know that immediately you get here for x in d omega. And then G is a continuous function. Once it's continuous function, so by assumption, one is solvable. Assumption, one is solvable. So that gives you a harmonic U, and hence it is subharmonic. A harmonic U. So there is therefore subharmonic. And then of course U psi also, U psi is equal to G psi in the limiting sense. Okay, that's equal to 0. So that condition is satisfied, subharmonicity is satisfied, and by maximum principle, which I will not state here, maximum principle, G is a negative function. You see, maximum principle, you get U is negative for all x in omega bar minus psi. That implies U is a barrier at psi. Barrier at psi. Okay. I thought of giving some examples, but it may take a little more time. So maybe I will do that in the next class, even though we are going to have a Newtonian potential. To some remarks of 5 to 10 minutes I require, so maybe this lecture will not be able to do it. So but the main idea from next lecture onwards is to study the case of a Newtonian potential, because Laplacian U equal to 0 with U equal to G is completed, except some remarks which I will do it here. But then Laplacian U equal to F with U equal to G, and which we will start studying from the next class onwards. Another 4 or 5 lectures we will do this one. So we'll stop here. Thank you.